Hello, my name is Orion Ning, and today I'd like to talk about my work with Anupam Ray and Ben Safdi on axion lines from nuclear de-excitations in galactic stellar populations. Our headline conclusion is that we find no evidence for axions in X-ray searches for monoenergetic axions, which are sourced from nuclear isotope de-excitations amongst stars in galactic stellar populations. Here we show the 95% upper limits and 1-2 sigma containment bands under the null hypothesis on the combined axion-nucleon and axion-photon couplings from our two most stringent searches, that looking for axions produced from iron-57 transitions in the M87 and M82 galaxies. Excitingly, our results lead the constraints for ultralight axions coupling to nucleons and photons below around 10 to the minus 10 eV. Our search begins by taking the fact that axions can be produced from the de-excitations of thermally excited nuclear states. Here we show a simple example, a simple illustration for the well-known iron-57 transition, which emits a monoenergetic axion at a fixed energy of 14.4 keV, sourced from the de-excitation of the iron-57 excited state. Normally, these types of transitions occur at order MeV energies, but certain special isotopes such as iron-57, as well as a few others we explore in our work, can have low-lying keV level transitions. The reason this is important is because these axions can actually be abundantly produced in stars, which typically have X-ray core temperatures. Such searches have been done for the Sun using CAST, for example. However, we can take this several steps further. Even better than just the Sun, we can search for these lines from large quantities of even brighter and even hotter stars in galactic stellar populations. We thus search for these axions in various galaxies such as the M82, M87, M31, and the Milky Way galactic center, which were interesting for other axion-related studies listed here searching for different couplings. Each galaxy has interesting qualities. M82, for example, is a prototypical starburst galaxy hosting many young hot stars. M87, nestled in the Virgo cluster, benefits from strong cluster magnetic fields, and M31 in the galactic center are, of course, close by. In all of these cases, we search for the nuclear de-excitation axions converting to X-ray photons in the host galaxy's magnetic fields. The search is relatively straightforward. Very briefly, we show here the axions produced from these de-excitation mechanisms across various isotopes and galactic targets. The isotopes we found that were the strongest at the level of axion luminosity were iron-57, nickel-61, and germanium-73, although as alluded to earlier, at the end, ultimately iron-57 ended up giving the strongest constraints. These axions, again, convert to X-ray photons in magnetic fields of the host galaxies, whose conversion probabilities, pulled from either illustrious TNG cosmological magnetohydrodynamical simulations for M82, M87, and M31, or from parametric models for the Milky Way, are illustrated here with their corresponding uncertainties. We take care to take the more conservative choices of these conversion probabilities in our fiducial analyses, shown in bold lines. Finally, these resulting X-rays are searched for in archival NuSTAR data of the galaxy targets, and the signal, an example of which is shown in purple here, would show up as a broadened line signal at the relevant de-excitation energy after being put through the detector response. It is this potentially prominent signal that we search for in our work here. Again, we find no evidence for axions from our various galaxies and isotopes surveyed, and instead set leading constraints on the combined axion-nucleon and axion-photon coupling, primarily from searches for iron-57 in M87 and M82. This is a great demonstration of yet another example of how powerful stellar populations can be in searching for axion-related signals and constraining important axion parameters. We hope this continues to serve as inspiration for related axion searches in the future. Thank you for listening, and we hope you check out our paper.